This is a question dealing with projectiles going from ground to ground. And this question says a projectile is launched with a speed of 10 meters per second at an angle of 25 degrees above the horizontal. Find the time that the object spins in the air and find the range of the flight. Okay, so we have a projectile launched and it's going to go in the air like this. It's going to mirror its path and come all the way back to the ground. So let's draw this situation. So if I guess I can draw it over here. Let's do it like this. And I'm going to draw the variables over here so you can see them like that. Okay, so I have a projectile and it's going to launch in the air like this. So what is significant about this particular problem? Well, the first thing is that we're going to be going from ground to ground. In other words, this projectile is going to go through the air. It's going to go all the way through the air, and then it's going to symmetrically come across and go back into the ground like this. And when it goes into the ground, it's going to have this symmetrical looking shape to it. Okay. What I mean by that is that the angle is going to be the same here as it is here. So if I come over here and I write in the angle here, this is 25 degrees like this. That means this one is going to be 25 degrees here. 25 degrees. So that gives us a lot of that gives us a big advantage in terms of working with the numbers. And I'm going to show you there's a very fast way to solve this without doing too much work. We do have symmetry here. So some people will solve this problem and they'll actually come to the max height here. And they'll actually just find the time to the max height and then they'll double it to get this time here. But you don't really need to do that. I'm going to show you why. Okay, when we have a problem like this, we have components, right? We have an initial x and an initial y. So right here I have my v initial y. And I have down here, I have a v final y, but these are going to be equal and opposite in magnitude because the problem is symmetrical. So this is v final y. I also have an x value. I have a v initial x, and this never changes throughout the flight because there's no acceleration in the x. So I have my v initial x here. Okay, and I have my v initial, which is this black arrow. And remember, when you're looking at an object, you don't see the y component, you don't see the x component, you just see the velocity. So if you catch a football, let's say you were catching a football, you don't catch the x or the y, you actually just catch this black arrow. So that's the speed that you see, that's the speed that's creating the kinetic energy of the object, but we break this up into components so we can work with them. So when we have a projectile problem like this, we like to do a table here. And before I even do any equations, I really like to get this table set up just so we can start analyzing the problem here. Put it right here. Okay, so we have some common variables in play here. And the first one's going to be my acceleration. So I have an acceleration in the x, and that's going to be 0. And I have an acceleration in the y, that's going to be negative 9.8. So I have a v initial in the x, I have a v final in the x, I have a delta x, which is going to be the range, and I have the time. Over on this side I have the same thing. I have a v initial y, I have a v final y, I have a delta y, which is the displacement, which is what we're gonna need to use a few tricks here to solve this problem. That's going to involve this. And I also have a time here. Now these two times, they are going to share the values. So if I find the time of one, I can use it over here for the other. But when I start any projectile problem, these two situations are always true. I always have a 0 acceleration in the x, and I always have negative 9.8 for the y. So the question we have to ask ourselves is, what do we do next? And what are we trying to do in our strategy to solve this problem? Well, the first thing we need to do in any kinematics problem is we need to find three variables on this side of the equation. In other words, when we're dealing with the y and we have a constant acceleration, we need three variables. So I found one by default, but there's actually another one right away that you can solve, and that is this delta y is 0, because this ends up in the same spot. If I make my x and my y here, it ends up in the same spot on the y here as it does here. In other words, it starts at 0 and it finishes at 0, so my delta y is 0. Okay? So right away that gives us two variables. I have not even done any calculations, but I can just start setting this problem up. Now the next thing we have to do is we actually have to start finding these values. So my v initial was given to us, and that is going to be 10 meters per second. And I need to find this v initial x. So the v initial x is going to be v initial cosine 25, because cosine is the x value when the angle is taken to the horizontal. So it's going to be 10 times cosine 25. And that's going to give me about 9.1, let's just say, meters per second. The next thing I have to do up here is find my v initial y. So my v initial y, which I'll rewrite it up here, just because we don't have enough space, is going to be 10 times the sine of 25. And that v initial y is going to be about 4.2 meters per second. So this is always important in a projectile problem. We have to split up our components. We have to know what the initial x is, and we have to know what the initial y is. Because the only language that we speak is x and y in terms of the equations, because I've defined my axis like this, right? Okay, so we can go back over to our table here, and now we can start to fill in a lot of information. Well, my v initial x is 9.1. My v final x is also 9.1, because this is no acceleration along the x. Okay. My v initial y is 4.2. But guess what? My v final y is going to be just negative 4.2. You see that? I'm going to write this in blue just to emphasize that, because it's pointing down and we have symmetry. Okay, so this is symmetry. These two right here came about from symmetry. So that's why this problem is really interesting, because with very few calculations we can begin to solve a lot of information about it. And so what were we looking for in the beginning? We were looking for the time, and we were looking for the range. Okay, so we were originally looking for the range, this, and we were originally looking for the time, which is this. Okay, so that's what we were originally looking for. Look at all this information we have now. Just by analyzing how this problem is set up, I get all of these variables, and now I'm only down to two variables now, right? So what equation would we use? We know that there's a lot of equations in kinematics. People love to use, delta y is v0t plus 1/2 at squared, or v squared equals v initial squared plus v squared equals v initial squared plus 2a delta x. Those are the two longer equations. But I would suggest to you that when you have four variables like this, you should always look for the simplest equation to use. The more variables you have, the easier the equation you can use. So let me write all of these out for you. Okay, so I'm going to write these out for you here. Or I have written these out for you here. These are all the kinematics equations in the y direction for a constant acceleration. So just to review, we have delta y is v initial plus v over 2 times time. V final is v initial plus at. Delta y is v0t plus 1/2 at squared. And v squared equals v initial squared plus 2a delta y. People really like to go to these equations a lot, especially when we're dealing with projectiles. But in this particular case, we don't even need to look at these. Okay? Why? Well, we have a lot of information, right? We have four variables over here, and I really only need 3 variables to start solving these. So when I have 4 variables, you should pretty much be looking to these 2 equations to figure out what's going on here. So what I'm going to do is I'm going to look at this equation right here. V final equals V initial plus AT. Okay, so V final equals V initial plus AT. So my V final in this case was negative 4.2. My V initial equals 4.2. And my acceleration is negative 9.8 times time. So I'm just plugging everything in there. What is my unknown here? My unknown is simply going to be time right here. You see that? That's my unknown. That's what I'm looking for. So I can combine these equations over, and a lot of times people look at this equation and they say, well, the 4.2s are going to cancel out. Well, really, they don't cancel out because this is a negative, and this will become a bigger negative when you subtract it over. So when I bring that over, I'm going to get negative 8.4 equals negative 9.8 times time. And then when I solve for the time, I'm simply going to get negative 8.4 over negative 9.8. And now you see what happens to the negatives. The negatives will actually go away. And I'm actually going to get a physical value for time. And when I say physical value, I mean just a real number, right? Because sometimes we can get negative numbers for time when we're dealing with a quadratic equation. And in this case, we're only going to get this value here, which is just one physical real value, 0.86 seconds. So if I go back up here, I go to 0.86 seconds, 0.86 seconds. So now I've found the first thing I'm looking for, time of flight. And now I want to find the range. And I look over in my x direction. And in my x direction, I only have one equation. It's just this one. Vx is delta x over delta t, right? Because there's no acceleration, right? So this one has no acceleration, right? And this one has a constant acceleration. We just did. So for no acceleration, it's a very easy situation to deal with. I just have this equation. And what am I looking for? I'm looking for the range, which is delta x. And I solve for delta x. So delta x is going to be Vx times the time. So we'll go over here. We'll just do it over here. Delta x is going to be Vx times the time. So delta x is going to be 9.1, which is my v and the x, times the time, which is 0.86 seconds. So that's going to give me a total range of 7.8 meters. Okay, so that's my range there. So 7.8 meters is the range. 0.86 seconds was the time. So now when we go up here to our chart, we can just fill in the final values here for range and time. And we can clearly see that we have solved the question here with very little actual calculations using the equations. We actually just looked at the situation and we figured out what was going on in terms of the symmetry of the situation, because again, this started from here, it ended up at the same height, so the delta y was 0. We had the initial y here, it was a mirror basically of this v final y here. So we were able to start getting all this information, and then we knew the acceleration is always negative 9.8. We know the acceleration is always 0 for the x. So all of this information here, this was all, this was all obtained just by reasoning through the chart here. You see this here? We had to do the one little calculation here for the v initial y, but really we just multiplied it times sine 25 to get that. And then we were dealing with very few math equations at the end. We had this one equation here, v final equals v initial plus at, to find the time. And then we just had delta x equals x times time to find the range. So this is a good example of how reasoning through the situation can greatly simplify what you have to do at the end. I hope that you enjoyed this video, and there's going to be more videos on projectiles, so please tune into this YouTube channel if you want to see more. I'm Shane Smillian. Thanks for watching, and I'll talk to you soon.